Remember this example of finite automaton, which recognizes strings that end in 1, 1. For this automaton, it's clear that if the machine will read at the beginning the digit 1, it will move from the state A to the state B. But if it reads the digit 0, it will stay at the same state A. For this, we say that we have only one way from the state A with the symbol 0. Also, we have only one option. If we will read a 1, the machine will always go from A to B. Also, from B, if we'll read a 1, it will go to C. If we'll read a 0, it will go back to A. So for this machine, it's deterministic. That means we have always only one way, exactly one way, from a state to another state when we read a symbol of the alphabet. Note here we can draw another machine that recognizes the same language, say all the strings that end with the substring 1, 1, but with less number of transitions or less number of arcs. Here we notice that we have used the digit 1 here and here. So it says that from A, if we read 1, we may go to A, we may also go to the state B. So as we see here, we go from A to B with the symbol 1 for this case. In another case, we may transit from A to A with the symbol 1. And for these two cases, if we go from A to A with the symbol 1, after that, if we have another one, we may transit from A to B or again from A to A. So this introduces to the non-determinism. A non-deterministic finite automaton is a machine that allows to have 0 or more transitions with the same symbol from the same state. Unlike the DFA, where we have always only one transition with the same symbol for the same state. So for non-deterministic finite automaton, here when given a string, the machine will try all the possible options that it has. If one of these options end with an end state, then the machine will accept the string. Let's simulate the two machines with the string 1, 0, 1, 1, 1 to see if it's accepted. So for the deterministic finite automaton, we have only one next state when reading a symbol. But here we may have different options. So we'll draw all the possible options. For the one here, the first symbol here, if we are in the start state A here, we have two options, either to stay at the same state A or to go to the state B. So we draw these two options. For the DFA, we have only one route here. From A, we'll definitely go to the state B. Then for the second symbol here, 0, with the deterministic finite automaton, it's clear that from B, when we read 0, we'll go to A, so we have only one option. Here also we have only one option. If we are at the state A and we will read 0, we'll stay at the same state A. From here, we don't have any possibility with this 0 since there is no arc here going out of B with the symbol 0. So we may see this as a tree where this branch dies here. Now for the third symbol here, 1, with the DFA, we'll transit from A to B, and here from this A again we have two options, either to stay at the same state A or to go to the state B. So we draw the two options here and we'll follow each branch of the tree with the other symbols of the string. Once we finish tracing all the symbols of the string, if we have any root that leads to a final state like this one, we'll say that the machine here accepts the string. Even if there are other roots that don't accept this string, one way that leads to an accept state is sufficient here to say that the string is accepted. For the DFA, it's clear that we have only one way, and this way leads to a final state, so we'll say that this string is accepted. We have another option here in a non-deterministic finite automaton, which is the epsilon transition. Epsilon transition here means that we may transit from A to B without reading any symbol of the alphabet. So epsilon here will be added to the non-deterministic finite automaton as a symbol, and if we use it on one arc, the machine may go from one state to another without consuming any symbol of the string that the machine is running on. These concepts lead to formally define what is a non-deterministic finite automaton. So simply an NFA may be written as a 5-tuple. So here we'll have a set of states, a set of input alphabet, and an initial state, a set of final states, and a delta transition function. So here it shows that if we have a state from Q and a symbol of the alphabet, the result or the next state will be a subset of the states Q. That's why we have written here power set of Q. And also here we used sigma epsilon, which means that we may have symbols of the alphabet on the transitions. Also, we may have the symbol epsilon. Remember that the power set of Q is the set of all the subsets composed of the states of Q. So if we have, for example, two states in the set Q, the power set of Q will be empty set, a set containing only the state A, the set containing only the state B, and the set containing all the states A and B. So in general, if we have n states, the number of the sets in the power set of Q is 2 to the n. Let's take an example. For this machine, the set of states is A, B, and C. The alphabet is composed of the symbols 0 and 1. The initial state Q0 is the state A. The only final state here is C, so F equal set containing the state C. For the transition function, we may draw a table that recapitulates all the transition function here. It states that from the state A, if we read 0, we'll stay at the same state A. So we'll write here set containing only the state A. If we read 1 from the state A, as we see here, it's either A or B. So we have written here the set containing A and B. If we read an epsilon, that means if we read nothing, no symbol there is read, we may go to the state B. Then from B, we have no arc going from B with 0. So we write here empty set. With 1, the next state will be C. And with epsilon, there is no arc, so it's empty set. From the state C, we don't have any arc going out of this state with any of these symbols, so it's empty set in all the columns. Here we remark that inside this table, we are always writing one of the subsets here contained in the power set of Q. Of course, it's not tremendous to use all of these subsets, but it's important to see here that every set of states written here is one member of the power set of Q. Let's take another example of a non-deterministic finite automaton, and let's write its formal definition. We have here the set of states A, B, C, and D. The symbols here used are X and Y. The initial state is A. The final state is the state B. For the transition function, we may write here the transition table showing that from A, if we read the symbol X, we'll go to either B or C. So we will write here the set of states B and C. From A with the symbol Y, we will write here only the set containing the symbol A. With epsilon, there is no arc going out of this state, so we'll write here empty set. From B, we have only one arc going from B, which shows that we may transit to D without any symbol. So we'll write here in the column epsilon the set containing only the state D, and so on. Another example here showing that we have 4 states also. We have the set of symbols of the alphabet 0 and 1. Q0 is the state A. The final states here are C and D. And here we didn't use the symbol epsilon, so we'll write the transition table with 2 columns showing the symbol 0 and the symbol 1. And here it shows that we have 4 states, and inside each cell it shows where we are going from this state reading this symbol. Let's now define a computation in the context of a non-deterministic finite automaton. So if we have an NFA M and a string W, which is a list of symbols of the alphabet, we will say that the machine M accepts the string W if W can be written as a set of symbols V1 through Vn, where Vi is in sigma epsilon. These Vi may be a symbol of the alphabet or epsilon, and there is a sequence of states R0 through Rn in Q, such that the first state here is the initial state, and we have Ri plus 1 is one member of delta of Ri Vi plus 1 for all I going from 0 to n minus 1. And if we finish with Rn in the set of final states, we'll say in this case that the machine M accepts W. Let's take an example here. We'll go back to the machine that recognizes the language of all strings, all binary strings ending in the substring 1, and let's show if 10111 is accepted. So we'll start in the state A, then from A with the first symbol 1 here from the string, we have reached, or we can reach the state A. Then from this state we can read the symbol 0 here, the second symbol of the string, and we may reach the state A. From this state we may read the third symbol 1, and we may reach also A. From the state A we can read the fourth symbol 1 here, and we have the possibility to reach B. And then from B we may read the last symbol 1 here, and we reach the state C. Since C is the final state, we'll say that the string is accepted. Here we have shown only one way that leads to an accept state, the way that guarantees that 10111 is accepted. But in general, we can draw in a tree all the possible routes when we run a machine on a specific string. So in this case, we'll say that we have to start at the start state A here, and we will draw all the possible options when reading one symbol of the alphabet. Then we have to look if we have a route in which we finish reading all the symbols of the string and we finish in a final state. In this case, we will say that 10111 is accepted. Here we care about finding only one way leading to the final state. It's not a problem if there are other routes that lead to a non-acceptation of the string. The essence here is to find a way that leads to an accept state. So in general, for the case of a DFA, we will have a deterministic computation in which we will have always only one next. And for a non-deterministic computation, from any level here, we may have different possibilities, different options, different next state. We will draw all the possible move through the machine, and we will look if there's a route in which we will reach an accept state. And we'll finish now by showing that we have a very important theorem that states that every NFA has an equivalent DFA. The idea of the proof here is to show how to construct this DFA given a non-deterministic finite automaton. And an important corollary here can be stated, which gives the important result here that a language is regular if and only if there's a non-deterministic finite automaton that recognizes it. We'll show next how to convert non-deterministic finite automaton to an equivalent deterministic finite automaton.